Welcome. Let us begin today by considering the effect of temperature on the equilibrium constant. We have seen equilibrium constants for reactions and their relationship to the standard chemical potential in the previous class. In this class we will start looking at the effect of temperature on the equilibrium constant. Let us first recognize that mu I naught, the standard chemical potential, this is a part of mu I equals mu I naught plus RT ln Fi or equivalent. Mu I naught is only a function of only temperature. Therefore, this equation 618 minus RT ln Kp equals sum over I nu I, the stoichiometric coefficient, times mu I naught. This is what we had derived in the last class, and this is also the relationship between the equilibrium constant and the standard chemical potential. This equation let us rewrite by recognizing the functionality of T as ln of Kp. Let us take T to the other side, RT to the other side, minus 1 by R, there is also minus here, sum over mu I naught by T. We have, since mu I naught is a function of T, let us group this T along with mu I naught to enable further manipulations with much ease. Let us call this equation 629. This is why we did it. We are going to differentiate this expression, and when we differentiate, it is good to know the functionalities clearly, and that is why we had grouped it with mu I naught. Mu I naught by T is inside the sum here, the product is nu I mu I naught by T. If we differentiate equation 629 with respect to T, in fact that is what we are looking for. We are looking for the effect of temperature on the equilibrium constant. The equilibrium constant that we have considered first is Kp. So, we get d ln Kp dt is nothing but minus 1 by R sum over nu I. Nu I is just a stoichiometric coefficient, not a function of temperature. Therefore, the function of temperature is mu I naught by T alone. Therefore, this becomes d dt of mu I naught by T. Let us call this equation 630. We know from equation 4.1 is just the definition of the chemical potential, that mu I equals mu I naught plus RT ln P y I. We are still with the perfect mixtures. So, mu I equals mu I naught plus RT ln P y I. Let us divide this equation throughout by T, then we get mu I by T equals mu I naught by T plus of course R ln P. I have just split this term, this is ln of A into B, that is ln of A plus ln of B, and there is an RT that is multiplying. So, you have RT ln P plus RT ln yi, and RT ln P by T gives you R ln P plus similarly R ln yi. This is equation 631. Now, if we assume conditions of constant pressure and constant composition, quite easy to see that pressure remains a constant and the composition as represented by the mole fraction, that remains a constant, and therefore, the derivative with respect to T of mu I by T, dou T of mu I by T at constant pressure and constant composition, here indicated by Ni, but here indicated by Yi. The constancy just mean the same, but let me explicitly write Ni here. So, dou T mu I by T at constant P Ni on the right hand side becomes d by dt mu I naught by T, because that is a function of only the temperature. I have taken the total derivative here, and these two are constants, and therefore, they are not functions of temperature, and therefore, their derivatives go to 0. They are constant values as far as temperature variation goes, and therefore, they can be taken as 0. Let us call this equation 632. Now, using equation 515, which is, remember, this is the third equation that we derived when we took a detour in the module 5. Now, it is coming in handy. Dou mu I by t dou t at constant p n I, we have already shown that as equal to minus of h I t hash, the partial molar entropy, divided by t squared. So, on one hand, from equation 515 we have dou mu I by t dou t at constant p n I equals minus h I t hash by t squared, and as a part of this equation we have dou mu I by t dou t at constant p n I equals d dt of mu I naught by t. Therefore, we can, since the left hand sides are equal, we can equate the right hand sides, and therefore 632 can be written as minus h I t hash by t squared equals d dt of mu I naught by t. Let us call this equation 633, and the right hand side is a total derivative, since mu I naught is a function of temperature alone. The partial derivative that we had taken earlier becomes a total derivative here. Now, equation 633 says something important. It implies that the partial molar entropy h I t hash is a function of temperature alone, and more importantly will have the same value for all values of the composition, because it is independent of the composition. Rather, it is a function of temperature alone, it is going to be independent of pressure or composition. Therefore, this will have the same value for all values of the mole fraction, even if the mole fraction equals 1. In other words, even if it is a pure component, this equation must be valid, and therefore, that is a powerful statement here. Therefore, for the pure component I, the partial molar value can be replaced by the molar value. This equation is anyway going to be valid. I am sorry, yep, here this equation 633 is anyway going to be valid because it is a function of temperature alone, and therefore, equation 633 can be written as minus h I by t squared. Instead of the partial molar value, I have taken the molar enthalpy here, minus h I by t squared equals d dt of mu I naught by t. So, remember, our aim was to get the variation of equilibrium constant with temperature. We are in the process. We should never lose track of whatever we are trying to do when we are in the middle of algebra. So, that way it helps us keep a sanity. Equation 634 is this, and therefore, equation 630 can be written as, equation 630 was nothing but the relationship, we had differentiated ln of Kp equals minus 1 by r, so on and so forth. This will come to you right away. If not, you can go back and look at equation 630. d ln Kp by t equals 1 by r t squared sum over nu I h I. Okay, let me just tell you how this comes about by going back a little bit. Equation 630 was this, d ln Kp dt equals minus 1 by r sum over nu I d dt of mu I naught by t. Now, we have a relationship of for d dt of mu I naught by t in terms of the molar entropy itself, molar enthalpy itself, that was minus h I by t. Therefore, if you take t out here, you will get plus, there is a minus 1 by t here. Therefore, when it comes out, you get plus 1 by r t here, and this would be nu I h I summed over all I, and that is what we have said here, coming up in a minute. d ln Kp dt equals 1 by RT squared sum over all I nu I Hi. So, this is a useful expression. This gives the variation of the equilibrium constant Kp with respect to temperature in terms of the enthalpies of the components involved in the reaction. This is something that you are used to doing right from higher secondary school. Sum over nu I Hi is how you found your delta H for the various reactions, if you recall that process, and you took the enthalpies of the products, summed them up, enthalpies of the reactants, summed them up, subtracted enthalpy of the reactants from the enthalpy of the products, and that formally written in a compact notation is this 1 by R sum over nu I Hi. Let us call this equation 635, and sum over nu I mi equal to 0 for a reaction written like this, as just mentioned, sum over nu I Hi. Recall that nu I is positive for products on the right hand side of the chemical expression, biochemical expression, and nu I is negative for the reactants on the left hand side of the chemical expression. This nu I Hi summed over all I is nothing but the enthalpy change in the reaction or of the reaction. This is equation 639, and therefore d ln Kp dt is nothing but equal to delta H by RT squared. So, this gives us an easy method of measuring the variation or estimating the variation of the equilibrium constant with temperature. Just integrate this expression, then we have the kind of relationship that we are looking for, or the estimate that we are looking for. This is equation 640, and this equation d ln Kp dt equals delta H by RT squared has a special name. It is called the Van 't Hoff's equation. Now that you have seen this, we have worked out a means by which we get the dependence of temperature, dependence on temperature of Kp in terms of the enthalpy of the reaction, and of course the temperature of the system and so on. What I would like you to do is, starting with equation 627, I will show you what equation 627 is. I would like you to derive the same expression or the same dependence for a slightly different equilibrium constant. As we have seen earlier, there are various equilibrium constants. You know this also from the higher secondary school time onwards. You have Kp, we have Kc, we have Ky, we have Kf, and what we are interested in here is Kf. This is equation 627. Start with this please, minus RT ln Kf equals sum over nu I mu I naught, and since this derivation, which lasted about 5 or 6 slides here with a lot of thought, I am going to give pretty much a lot of time for you, maybe about 20-25 minutes. Take that and derive the dependence, the temperature dependence of Kf the same way that we derived the temperature dependence of Kp. Go ahead please, take about 20 to 25 minutes and derive this. I am asking you to derive this here because there are some slight variations, and when you are faced with the variations, that is when you start thinking, and that is when you start understanding the various relationships a little better. The overall scheme is the same, but the details are a little different. So, please go ahead and derive this. Go ahead please. Okay. The relationship that we are looking for, you can check whether you got the same, is d ln kf dt equals again delta h by RT squared. Just check whether you got that. Okay. Now, this is, let us call this equation 641. If the temperature range is small enough so that the enthalpy change of the reaction can be assumed to be independent of temperature. In other words, the delta H is considered a constant in the range of temperatures that we are talking about. It is not exactly a constant, but its variation is small enough that the variation can be neglected. Then this equation 640 can be written as, when we integrate that, we are trying to find out a value of Kp2 given a value of Kp1. So, ln Kp2 by Kp1 equals delta H by R 1 by T1 minus 1 by T2. This is equation 642. This comes from the integration of equation 640. Let us go back to equation 640 to see how that comes about. This is equation 640 for Kp. You can do the same thing for 641 Kf. If we integrate this, so integral from T1 to T2, in this case it will be d ln Kp integrated from Kp1 to Kp2, and here it will be integral from T1 to T2 delta H by RT squared dt. If we do that, then this d power minus 2, and therefore it becomes minus d power minus 1, and so on the integral, and therefore you will get ln of Kp2 by Kp1 equals delta H by R 1 by T1 minus 1 by T2. The negative sign comes about because of the negative that arises as a result of the integration. We will call this equation 642, and this is actually the useful expression for finding out the temperature dependence of the equilibrium constant, or in other words, if one equilibrium constant at a particular temperature is known, then we can find another equilibrium constant at another temperature T2. Okay, let us see whether we are justified in starting up the next topic. No, I do not think we will have time for that. So, let us stop here for now. When we come back in the next class, we will take things forward.